In the wrong class, I solved this revision problem 2-6. It is being recorded. You can watch this later. Now we go to page 111. For today, this is all practice, and we will be dealing with calculation of the moment. So yesterday I mentioned there are two approaches for finding the moment. The first approach is if the forces are sitting in one plane, that's easy. All you have to do is to find the magnitude of the moment. And that is, if there are multiple forces, well, you can combine them or find out the moment due to each and add them, taking into account the direction. And then the unit vector is normal to the page. You don't have to worry about that. But if the forces are three-dimensional, the best approach is to pick a position vector to describe the force and then multiply them in a vector fashion. So today we do practices for both. So let's get into page 111 and see what we've got there. Or 111. Let's try 3-1, something about point O. Let's try C. That's something, or maybe we do B. So here I want to find the moment of the force about point B, about point O, rotation point. So how do we go about this one? Any suggestion? This is a coplanar force, right? Should we do this in a scalar or vector way? A scalar. And all right, so the one approach, which is a little bit trigonometric, you can find a line of action for this force. All right, so this is a line of action. And then if I can calculate the shortest distance between point of rotation and that line, all you have to do is multiply this force by that minimum distance. But that is a little bit of trigonometry. Maybe you don't want to do that. So something easier is to break that force into two components, x and y. So that makes this easier. So if I want to break that into components, this is the horizontal component, and that is the vertical one. All right. So the horizontal one is 500 multiplied by cos of that little triangle. That is 500 multiplied by 4/5, which is 400. 400, the unit is Newton. And what about the vertical one? The vertical is 500 multiplied by sine of that little triangle, which is 3/5. Okay. And that is equal to 300 Newton. All right. And now we have two forces. Each of these forces make a rotation with respect to the O. So starting with the horizontal one, what is the moment of horizontal force? So this force doesn't exist anymore. You don't consider it anymore because we already broke it into two components. So the horizontal one rotating with respect to the O. What is the shortest distance between line of action of this force and point O? Shortest distance. Nguyen? 1, is it? Just let me show you. I extend this one, that's a line of action for this, and then from point O, I draw a normal to this one. That's the shortest distance, isn't it? So the shortest distance from here to here is 1 meter. Can everyone see this? So the first component of the force. And is this going to rotate my system in a clockwise direction or counterclockwise? Counter, right? So the convention we had yesterday was counterclockwise, we took it as positive, and clockwise, we took it as negative rotation. So the horizontal component makes positive because that would rotate my system. Anyone knows why this rotates clockwise? So I made an analogy yesterday. Imagine this is a frame, you are trying to put it on the wall. And then you only put one tack pin at point O and you leave it like that. So this is not stable, it can rotate. It can rotate about point O. And then if you apply this force in this direction, your frame is going to rotate that direction. Can you visualize that? All right. So therefore, and then these are the conventions to remind ourselves that one of them is positive, the other one is negative. You could have made a convention in a different way, but this is just a convention. So we start with the horizontal one that makes 400 multiplied by the shortest distance, which is, this is Newton, multiplied by 1 meter, positive. And what does 300 do? Does it rotate my frame clockwise or counterclockwise? Darcy, is this clockwise or counterclockwise? Clockwise, and that's negative, right? So the next component is negative 300. And what is the shortest distance between line of action of 300 and point O? 2. That's 3, take away 1, this is 2. Well done. So that's 300 Newton multiplied by 3 minus 1 meter. And yeah, that's it. So the total moment about point O, that's just a magnitude. This is 400 minus 600, and that the outcome is minus 200 Newton meter. So can you verify the direction? Yep. Because the shortest distance between line of, let me extend this line for you. If I extend that, the shortest distance between a point and a line, you have to draw a normal from the point to here, right? So from here to here, that's 3 meter, take away 1, that is 2 meters. Yes, that's the shortest distance. Okay, so now I got, yeah, I got a negative. Can you verify negative is the correct sign? Flynn, can you tell me why negative is correct sign? I mean, if I didn't break it into a component, I would have gone with the original force, right? Does the original force rotate my frame in the clockwise or counterclockwise? Clockwise, negative. Anyone can see what? How did I check the answer? I checked the direction of the rotation. So breaking that into component, the direction of rotation is negative. But if we didn't break it into the component, still we had a force 500 acting above point O, which would have rotated my system in a clockwise, right? So that is to verify we got the right direction. Hopefully the magnitude is also correct. All right, if I want to express it as a vector, Chaisal, how do I express it as a vector? MO as a vector, that is minus 200, and what is the unit vector? If this is x, this is x, this is y. That's positive k. Can you use your right hand rule? So right hand, your 4 fingers go from x to y, and your thumb shows the direction of moment, which is projecting out of the plane. Okay? So that in clockwise, you go from x to y, your thumb is in positive z. That's plus 200k as a vector. Everyone can see? All right? Hopefully we get there. Question? Yes, yes, of course. Thank you for asking. All right. I mentioned if the forces are in plane, you don't have to worry about vector calculation. You just do a scalar calculation. A scalar calculation is force multiplied by shortest distance between line of action and point of rotation. That's hopefully no one has a question. Everyone is clear. But when you find the, well, moment is not a scalar. Moment is a vector. So all we calculated as minus 200, that is just magnitude of the moment. So if these forces are acting in plane, my system is going to rotate. And that rotation is a vector, is a moment. Moment, well, I mentioned about the right-hand rule yesterday. Three-dimensional things. So your forefinger, right hand forefinger, they follow the direction of the rotation, and your thumb shows the direction of the moment. So here I got X and Y horizontal, vertical, like so. So if I use my right hand, forefinger going from X to Y clockwise, the thumb is projecting out of the plane. So that is, let me draw this one for you, three-dimensional. So three-dimensional, that would be X, Y, and the third one is Z. So you go from X to Y, positive Z. So that is 200K with this coordinate system. All right? All good? Are you sure? Don't be shy. If you want me to explain it different way, I try. Well, both direction. What do you mean both direction? Yes, yes. Well, no, because you are resolving that force into two normal components. X and Y are arbitrary. We just chosen like those, but this was to help us finding the shortest distance between each force with the point of rotation. That was the only reason. Otherwise, like I said, I had to draw a normal from here. If I want to not project it, we could have left the force itself. So that is the line of action for the entire force. From this point, you draw a normal. That's the shortest distance. So it has a very small radius of rotation. And that is not easy to calculate. You have to do some similar triangles and trigonometry. So to avoid that, we did an alternative way. Just ignore that force, pretend that this is two forces here. So with this force, it's easy because line of action, normal, that's the radius of rotation. This one, shortest distance, 2 meters. So we could have done it differently. Or as you said, I mean, I could have written this one as ij, and with the ij, the product, the moment, I needed to construct that determinant, 3 by 3 determinant, and put R components, F components, ijk, and then find out the outcome of the determinant. So this is easier. It seems to be easier if you can relate with it. You have to shout. You have to shout. Well, this is. I mean, that according to that convention, that is negative. According to ijk, that is positive. Because I mean, I took my x and y like so. With those x and y, my thumb showing in the positive z. But with that convention, that is only to let you combine two different rotational directions. It could be opposite convention. That's just for helping you. Right hand rule, four fingers going from X to Y. The thumb shows the Z. X, Y, Z. Yep. All right. Everyone happy? Move on. Did I make a mistake? That is, yeah, this is 400, take away 600. That's the magnitude is 200. So that negative only tells you this is clockwise. But with this xy, that would be positive k. Yeah? All right, let's go to page 111, fundamental problem 1 to 6. And here, I think everyone wants to have, do you want me to do one more of these before we go to the next page? Yeah, one more of these. Let's try this one, which is kind of complex. It might look complex, but it's not. So okay, let me tell you how many approach we have here for solving. This is even more important than the solution. Please listen carefully. So here, I want to find the moment of the force with respect to the O. How many approaches are there? Two approaches. The first approach is because the force is two-dimensional, the easiest approach is to find the magnitude of the force, and the direction we already know. The direction of the moment is either out of the plane or inside the plane. It is all the matter of how you define your xy. If you define your xy like that, this would be negative k, going inside the plane. So if I take my coordinate system like so, x, y, so this force, and that's a frame. This frame, I forgot to put two pins. I only put one pin here. So that frame is going to rotate. With this frame, if I apply that force, this is passing above point O, making that rotate like that. So I go from x to y, that goes inside the plane. That's negative k. So if that was clockwise, that was out, projecting out. This is rotating that way. So from x to y, that will count goes inside. With this would be minus k. So that is one thing we can deal with that in a scalar fashion. It's still a scalar. How do you find the magnitude? The magnitude, there are two ways to find it. First, I find the line of action for this one, and then find the shortest distance between that point and line of action. This is to project from here to that line. That is a little bit trigonometric. So again, easier approach is to break that into two components, because when I break that into two components, I easily find with that component, line of action, shortest distance to this. With that component, line of action, shortest distance to that. No calculation. So which one you want to do? The second one? All right, so let's do the second one. Here, first, I break that force into two components, horizontal, vertical. So the horizontal is 500 multiplied by 4 over 5, and horizontal is 503 by 5. So this becomes 400, and that becomes 300. Everyone happy with that? Okay. So next thing, I find line of action for horizontal. That's a line of action. And then what is the shortest distance between point of rotation and that line of action? You have to draw a normal from here to here, a normal here to there. So Barnaby, what is that length, the shortest distance? 3. Yes, well done. So, and is this going to rotate my frame clockwise or counterclockwise? Okay, so we just assume that clockwise is negative and counterclockwise is positive. So in that, my magnitude of moment, the first component is 400 times 3. That is Newton, this is meter, and the sign is negative because that's clockwise. What about the vertical one? The vertical one, again, you draw a line of action. That's the line of action for 300, right? And then from point of rotation, you draw a normal to that line of action. What is the length? What is the distance? Who can tell me what's the distance? 1 meter, right? And is this clockwise or counterclockwise? So again, that is counterclockwise because O is in the right-hand side. So that would rotate my frame counterclockwise, doesn't it? Come on, that force, this is the pin, fix here, counterclockwise. That's positive. So that is plus 300 multiplied by arm of rotation is 1 meter. And the outcome is that is minus 900 Newton meter. Okay, who can verify that this is the right sign of rotation? I can. That is how you do road. Imagine it was not broken into two components. You had to find the line of action for the original force. So let me extend this one. Does it go above 0.0 or below 0.0? Above 0.0. So how does this single force is going to rotate my frame? That would rotate my frame in a clockwise direction. Clockwise is negative, isn't it? Make sense? So that is to verify that what we did, at least from the sign point of view, is correct. All right, so now I find the magnitude. So that minus 900 shouldn't confuse you with the I and j, k. This is only, that minus 900 is a clockwise. But then if you want to express that in the I, j, k, you need a coordinate system. Let's take this coordinate system. With that coordinate system, my system, the direction of the rotation is what? The direction of rotation is clockwise, isn't it? So let your forefinger of right hand rotate clockwise, and your thumb shows what? Inside the plane. Inside the plane. So inside the plane is the opposite to the k with that coordinate system. So that gives you m as a vector, m as a moment. That is minus 900 k with that coordinate system. Which one? The components or the force itself? Okay, 400. 400 with respect to this point. That is a frame you put in a wall, put a tack pin here, and then you push it from here. Does your frame rotate this way or that way? Clockwise. And clockwise, we assume that is negative sign. Yeah? But with this one, the frame is being pinned to the wall, and you push it like that. The frame would rotate counterclockwise. That's positive.
Still don't understand that.
Right hand.
Yeah.
Right hand rule is a convention, and that is when you have three coordinate system mutually perpendicular. That is like so. Let me draw it for you. So that is a three coordinate, which are 2y2 perpendicular. That is x, this is y, this is z. This is positive I, positive j, positive k. All right? Now, the right-hand rule is to tell you when a vector is acting on an xy plane, right? The rotation would be normal to that page. So is this out of the plane or inside the plane? Is this upward or downward? Right-hand rule tells you, okay, so with your four fingers, follow the direction of rotation. So what kind of rotation this system of force does? This would be that coordinate system. It make my system rotate like so. So your thumb is showing toward yourself, coming out of the plane. With this coordinate system, out of the plane is positive k. So, sorry, with this rotation, your right hand rule shows this rotation is inside the plane, opposite to the z component. So you try that. This is my right hand rule. That would rotate this way, right? So with my hand, I rotate this way. This is going inside the plane. Inside the plane. So inside the plane is negative k, because positive k is outside the plane. Yeah? All right, let's do more practice. Don't panic. You get there. And now we go to page 112. Choose something between 1 to 6. Do you want simple, medium, difficult? Medium. All right. Everyone happy with medium? Okay. Let's do, for example, 3-4. Okay, this is very same thing. The forces are coplanar. They are sitting in one single place, two-dimensional forces. The best approach for two-dimensional forces is what? That is to find the magnitude, and the unit vector is either k or minus k. That is outside the plane or inside the plane. Nothing complex about it. I mean, you have a frame, you want to put it on the wall, and your frame is only rotating this way or that way. If that rotates this way, depending what your x and y are, so this is the third one, inside the plane or outside the plane, plus k minus k. That is a shortcut, because if you want to do it in a general sense, moment is a vector, and that moment, I just remind you from energy and motion. How did we calculate the moment? The moment was as a vector, m as a vector, that is a position vector, cross product by force. And how did we do that? You have to construct a 3 by 3 determinant, I, j, k, and put rx, ry, rz here, fx, fy, fz. And then you have to calculate that one. But because this is two-dimensional, we want to take a shortcut. Shortcut is, don't go through this complication. Find out the magnitude. And magnitude, one simple point you have to remember, when you are finding the magnitude, this is not r times f. This is d times f. And d is the shortest distance between the line of action of the force and the point of rotation. So that is the only trick. If you manage to find the shortest distance, we can calculate the magnitude of moment by the scalar fashion. Simply shortest distance multiplied by 4. Don't worry about the vectors. And then if I want to do that, right, I insist, let's not break it into the component. How do I do it? Okay, no problem. Let me find the line of action for this force. This is line of action. Everyone agrees? Now, what is the shortest distance between the point of rotation and line of action? You have to draw a normal from here to there. Normal, this is normal, okay? Okay, if I'm doing graphical solution, no problem. I plot everything on a scale and measure the shortest distance. No trigonometry is needed. But if I want to calculate that distance, it's going to be a little bit tricky. It takes some solving triangles, and you hate that, right? So again, we want to go through a shortcut. What is the shortcut? All right, the shortcut is, instead of handling the force itself, we handle the component of the force. The component of the force are one horizontal component like so, and one vertical component like so. So 40, what is the horizontal one? 50 cos 60 or sine 60? Cos 60. Huh? And what is the vertical one? That is 5 times sine 60, right? Yeah, 50. Yeah, thank you for that. 50. All right, so when I break that into component, I have to cross this. This doesn't exist anymore. We don't count it twice. All right, so the vertical force, is this going to rotate my frame clockwise or counterclockwise? Clockwise, that's negative. So that is minus 550 sine 60. And what is the shortest distance between this force and the point of rotation? Let's find it out. I draw a line of action, and then I draw a normal from here to that line of action. So tell me, what is that distance? That distance is 100 plus, from here to here, that is 200 cos 45. And then from here to here, that's 100, right? 100. Easy. That one is the rotation due to the vertical component. And then I have to add to it the rotation due to the horizontal component. The horizontal one, again, let me draw the line of action for horizontal, and then draw a normal from here to here to find out the shortest distance. So what is that short distance from here to here? Who can tell me what's that distance? Shaysal, what is that distance? 200 sine 45, right? So is this going to rotate my system clockwise or counterclockwise? Counterclockwise. Counterclockwise is positive. So the rotation due to the horizontal is plus 50 cos 60, and the arm of rotation according to Nguyen, that is 200 sine 45. Okay? And then when you add them, do you expect the outcome to be clockwise or counterclockwise? Can you cheat? The outcome, is it going to be clockwise or counterclockwise? That has to be clockwise because the original force would rotate my frame in a clockwise direction, right? So whatever that is, now say I'm lazy. Let's think that this is going to be minus 460 Newton meter, which means that's a counterclockwise. Sorry, clockwise. With that clockwise, if I take my coordinate system like so, x, y. So use your right hand, and with clockwise, your four fingers going clockwise, your thumb goes inside the plane. Is that plus k or minus k? Minus k. So if I want to write this as a vector, the moment would be minus 460k. Everyone understand? All right? Well, I was lazy to do the number crunching. I assumed that the outcome would be 460. But then, can you tell me that whatever that number is this going to be clockwise or counterclockwise? This is clockwise. The reason is the original force is like so. If you extend the original force compared to that point O, that would rotate my frame in a clockwise direction, wouldn't it? So that is why I put a negative here. That negative only tell you this is clockwise. But next step, you want to express this in terms of the unit vector ijk. Okay, with ijk, I take my coordinate system like so, xy. So with this xy, I plot this three-dimensional. This is x, this is y, x, y, z, right? So your right hand from x to y going in the clockwise direction. From x to y in a clockwise, that is opposite to the z. So that I put it minus 400k. So this minus 400 is not clockwise, counterclockwise. That is how the coordinate system has been selected according to ijk. All right, so you want to do something more with that page? One more example from that page, or okay? Let's go to yeah. What about C-8? C-8. All right. So very similar to this is very similar to the previous problem. The only difference is instead of one force, there are two forces. So what do we do with it? Well, the first approach is we find out the moment due to F1, F2, and add them together. And adding them is not difficult because, again, two forces are acting on the plane. So the outcome would be either normal to the page out, normal to the page in. So the outcome is either k or minus k. So in that sense, we can calculate the magnitude of moment by a scalar and then find out the unit vector just by rule of thumb. Otherwise, I mean, you're welcome to write this one as ijk, position vector, do the determinant multiplication. That is troublesome. The chances are you make a mistake in the sign somewhere. But this, at least you know what you are doing. All right. So again, I mean, I can use a medium way, not three-dimensional vector, not a scalar, but something simple. So this way, I suggest, I mean, there are many ways of solving the problem. So to me, the easiest way to do that is these forces in terms of ij, not ijk, only ij. So here I take my coordinate system like so. So with this xy, F1 is what? F1 is 500 cos the angle is 4/5, and that is positive I. And then the j component is also positive, that is plus 500 times 3/5, and that is j, correct? That makes 400I plus 300j. Any objection to that? That is F1, right? Happy, Mohammed? All right, let's do F2. F2 again, that is plus 600 cos 60I minus 600 sine 60j. Is that correct? So horizontal component, vertical. The vertical is pointing down, that is negative. The horizontal pointing toward the right, that's positive I. Just ask me if that's not clear, I explain again. Cesar, you don't seem to be happy with that. You want me to repeat? Happy? Yes?
Sir, for the angle, we're not taking the direction of the arrow.
Well, you just do a simple triangle. With a little triangle here, with this little triangle, you want to project the hypotenuse, find the adjacent term. What is the adjacent term? The adjacent term is 600, the hypotenuse multiplied by cos 60. And when you project, that is with the positive I. All right, so with the opposite side, that is 600 multiplied by sine 60, but the arrow would be showing down, which is with a negative j. That's how you do it. You have to be very fluent in solving a right triangle. How do you project the hypotenuse over the adjacent opposite? Please make sure you practice that enough, because from now on, in every problem, you have to make a judgment how to project the force and whether they will be positive I, positive j, or reverse. That is only a matter of practice. All right. So, are you happy we just add these two forces together? Okay, let's add them together. And someone with calculator can help me. F1 plus F2, that is 400 plus cos 6 is half, is it? So 60 sine, that is 0.8 multiplied by 600, and then negative plus 300. So that is minus, yeah. That is 100I minus 219.61J. You have to speak louder. No, that is 219J. 600 times sine 60.
400 plus 300.
Yeah. Sorry about that. This is 700. Yep, thank you for that. 700I minus 100. All right, now we pretend we have one single force which has, so let me cross all these, and then I replace the resultant force with the component. The x component would be positive. The x component will be a 700. And what about the j component? I have to plot that downward, shouldn't I? The j component would be, this is the resultant force. The resultant force, that is 219.61. Everyone happy? Okay. Now that is piece of cake, because the rotation due to the 700 with respect to the O. How do you find it? So you extend 700. This is the extension. The shortest distance between point of rotation and that line of action, what is it? 0.25. And is this rotating clockwise or counterclockwise? Clockwise. So the I component make a negative rotation, that is minus 700 times 0.25. And then the vertical one, does this make clockwise or counterclockwise rotation? Clockwise. Again, that is negative, right? Minus 219.61. And what is the shortest distance between that vector and the point of rotation? Is this plus that, 0.425. Yeah. Okay, so now we have two negative numbers added together that give you a negative number. That implies the system would rotate clockwise. So does this make sense? No, it doesn't. Because this force, does it pass above O or below O? So if I extend that one, is this below O, is it? Or above? I'm not sure if this is drawn on the scale. If that is on a scale, that would be below. That should make clockwise rotation. But then we found counterclockwise. How come?
No, sir. Below.
Below makes counterclockwise should be positive, but here we got a number which is negative. Okay, so again, 700 with respect to the O, clockwise. 219 with respect to the O, again clockwise. So both of them implying a clockwise rotation. So where did we make a mistake? This is positive. The second one is negative. Sorry? Oh yeah, yeah. I think I'm just ignoring the second force. That is, I'm only taking rotation due to that force, but there are two forces here. So the second force is making another rotation, isn't it? So this one is making, so that makes a counterclockwise. This one makes a clockwise. So the clockwise is stronger than the counterclockwise. So if you add these to rotational effect, the outcome would be clockwise. So that we are right. We are right. You didn't make a mistake. Everyone just got it? Okay. All right. So that's the difference between this problem and the previous one. The previous one, we only had one force causing the rotation. Here we have two forces causing the rotation. How did we handle it? We combined the forces together, make it one single force. That single force, we found the rotation due to that. That is, yeah, you're right. That has to be positive. Yeah, this is positive. 700 is making, yeah, clockwise, negative. You're right. So 700 with respect to the O, that makes clockwise, negative. 219, again make a clockwise, that is negative 2. Questions? Questions? No question, let's move on. You want to see that? Yeah. These are being recorded. And I think I'm going to upload them on YouTube so you can easily see them wherever you want. Remind me, I send you the link for watching them. YouTube might be more convenient than the Collaborate Ultra. All right, going to the page 114. All right, 114. Let's try. Okay, each of the three forces about point B. Okay, each of the three forces about B. So I call this the rotation of F1 with respect to the B. I call this M1. And then here again, we are talking about the magnitude of the rotation, right? So M1, that is the shortest distance of this line of action to point B. Again, we don't want to do the trigonometric solution. For that reason, I'm breaking that force into two components. So all the dimensions are provided in the XY coordinates, so this is easier to do it this way. So that is 250 cos 30, and this is 250 sine 30. All right, this way, I draw the line of action for vertical, and then the shortest distance between that line with the point B. What is the shortest distance? 3 meters. So everyone can see that. And it is going to rotate my frame. I mean, this time I put the tack pin at point B. So my frame is only hanging to the wall through point B. This force, does this rotate my frame clockwise or counterclockwise? counterclockwise. Yeah, counterclockwise. So here the frame is fixed here, and then you push it down about point B, that would rotate counterclockwise. That is positive. So that is equal to 250 cos 30, and the arm of rotation, or the shortest distance. From now on, the shortest distance, we call this arm of rotation. Arm of rotation. That is like a circular motion. That is the arm of rotation. And that is multiplied by 3. The unit is Newton meter. What about the horizontal component? The horizontal component with respect to the B, does this rotate my frame clockwise or counterclockwise? Clockwise. So that's negative. Yeah, just hold this here, hold this frame here, and then push the paper. The entire thing is clockwise. So that is minus 250 sine 30. And the arm of rotation, Ahmad, what is the arm of rotation for this force? With respect to the B, shortest distance? 4, yes? Okay, so just, we are lazy, we don't want to do number crunching. Do you reckon the outcome of this would be positive or negative? Let's find out. The outcome of that would be positive, right? Because this line is passing below B, that's going to rotate it. So whatever that outcome is, it will be rotated. Let's do the same thing for F2. Let's do that for the F2. Okay, this is tricky. I want everyone pay attention. I'm breaking that into 2 components. One component vertical, the second component vertical, horizontal. All right. Nguyen, tell me the vertical component with respect to the B. What would be the rotation? What is the shortest distance of the vertical load and point B? 0. It doesn't rotate. Well done. 0. Can you see? So from now on, if a force is passing through the center of rotation, it won't make any rotation. So the vertical one is easy. The vertical doesn't do any rotation. Only the horizontal one. Does it do a positive rotation or a negative rotation? That is counterclockwise positive. Well done, Chaisal. So for M2, that is equal to 0 plus 300 cos 60, and the arm of rotation is 4. So that would make a positive rotation, right? If you want to check that, so the original force was like so. This is the original force. With respect to the point B, that would make a counterclockwise because it's positive. And finally, the rotation of F3 with respect to the B. You have to say it by the closed eye. That's so obvious. What is the rotation of 500 F3 with respect to the B? Yeah. So let's not break it. Just keep it as it is. That's the line of action, right? So this is the line of action for 500. That is the line of action. And draw a normal from point B to that line of action. What is the shortest distance? 0. So the force multiplied by 0 doesn't make any rotation. So this, I mean, you could have seen it, because whenever the force is passing to the center of rotation, it won't cause any rotation. That is the case for the third force. The third force doesn't make any rotation. All right, I hope everyone got a kind of insight into this type of scalar calculations. All right, so life is never easy. Once you find something, once you understand something, you start with something more difficult. You know what the more difficult is? When we have to find the moment in a 3-dimensional sense. Three-dimensional sense. Hopefully you'll be fine. Page, yes, this one. So just ask me if any part of that you didn't understand, just ask, don't be shy. Let me explain this for you again. We didn't calculate it, doesn't matter. I just want you to understand the overall picture. Overall picture is more important than number crunching. Don't worry about the numbers. With the last one? Okay, last one. Now, you don't know anything about mathematics, you don't know anything about the mechanics. So here you have a frame, you put it on the wall, and then you pin that one here. This is very light. It won't rotate due to its weight. So this is hanging there. And from every point of this frame, if I pull it from here, that's the same point that the tack pin is. It won't make my frame rotate. Try it. Let me show it to you. Okay, so this is the frame. You know, this is the wall. I make a pin here, and then if I apply my force here, that's a very control. If I apply, that's a rotation. So if I apply my force, now this can rotate. Because it passes through the center of rotation. No matter what angle I apply, if that force is passing through the center of rotation, it won't cause any rotation. And then why is that mathematically? Because the rotation is the force multiplied by the distance. And in this scenario, the distance is zero. The distance of that line of action to center of rotation, you have to draw from that point to the line, it is zero. Zero multiplied, no matter how big you push it, it won't make rotation. Yes? Sorry? Shortest distance. Okay. That's a good way of putting it. Let's go back to the geometry. That's maybe, I don't know when you did the geometry. That is the problem. You have a line and you have a point. So my question to you is, what is the shortest distance? One person wants to go from here to this line. How can they make a shortcut? If they are dumb, they go this way, eventually they get to this line. But here they have to travel 10 meters. If they are a little bit clever, they do it like so. So this is shorter than that, they travel 8 meters. But if they are clever, they just jump to this line in a normal direction. So this is something 5. If they change the route, again, that becomes larger. If they change the route, that become larger. They become 12, right? So the shortest distance between a point and a line, that is to project from that point to the line. And that's what we did for when calculating the rotation. With every force, you want to find the shortest distance. This is the line. This is the point of rotation. What is the shortest distance between this point? You have to draw a normal from here to that line. And if you draw the normal is 4 meters. With this force, point of rotation A. So that's the line, this is the point. What is the shortest distance between here and you have to draw a normal from here to there. That's 2 plus 3, that's 5 meters. Is that correct?
No, I thought it was like that. So we copied from there to get to where.
It is how you define it. This is where your point of rotation is, when your line is. So the shortest distance from the point, normal to the line. Point, normal to the line. Okay. So page 1, let's see, we have page 113, page 113. All right. Let's try 3-11. This is a 3-dimensional problem. I don't know, maybe three-dimensional is easier for you because that's more difficult to make mistake. Sometimes two-dimensional is just, you have to make a lot of judgment, and judgments. All right, here, no Mickey Mouse stuff. Here we want to find the moment as it is. Moment is not a scalar. Moment is a vector. So take the bulls by horn, what they said. So I want to find the rotational force F with respect to the O. That is, I call this MO. And that moment is a vector. So that vector, let me explain to you what that is. That moment is a position vector multiplied by the force. So hopefully no one is confused about the force. I mean, force, you know how to represent it, but the position vector could be a little bit confusing. Please listen very carefully. So what is the position of vector here? Is this the position vector OB? Is this OC? Or let me extend this one. That's the line of action for the force. So this is the line of action for the force, right? So how many points are shown in the figure? Point C, point B, both of them are sitting located on the line of action, right? So what if I have another point here? I call this one D. Could I take my position vector OD? So the question is, that position vector here, should I use OD? Should I use OB? Or should I use OC? Which one?
Any of them.
Any of them. Any of them, right? If you are doing that by vector, don't worry about the shortest distance. Vector, you don't need to worry about the shortest distance because IJK would take care of cutting that short. They make sure you get the shortest distance automatically. But then this is a matter of how smart you are. Yes, three of them are the same, but are they of the same ease? Which one is easiest? Well, D is not good because we don't have any dimension for it, right? I don't know where the hell D is. The location, the coordinate, I don't know. If I did, I could have used it. But the 2 point which I could use is OB or OC. So which one is easier? OC is easier or OB? OC. OC only has a X component, isn't it? But OB, you have to construct this in a three-dimensional way. So for that reason, I write, well, first of all, I have to find F. No question about that. How do I find F? F is the magnitude of F, 600, multiplied by its unit vector of F. And what is unit vector of F? That is unit vector of BC, isn't it? Yes, they share the same parent. And unit vector of BC, you have to construct the BC as a vector and then normalize that to the unit vector. You divide that by the length of that. All right. So maybe after all, the vector is not that difficult. If you understand it, it's just you could make mistake in putting things in the determinant and so. And during the class, I told you that there are two ways of finding. First, you calculate the determinant. You always can make a mistake with the sign. But then I gave you a formula. That formula has all the sign in it. But that is difficult to memorize. And you don't have to memorize it. In the exam, that's an open book. So if you have to choose between using the closed form formula, the mathematical expression, or the determinant, my answer is go for the formula. Because with that, you don't make a mistake with the sign. And you don't have to memorize it. That's included inside the formula sheet. maybe what you do from now on, try to have your own formula sheet and get familiar with it. During the exam, you are friend with your formula sheet. You know how to use it. If I just break a formula sheet to you during the exam, so, oh, what is it? I don't understand it. Try to have your own on a piece of paper, laminated or whatever, and then every problem you solve, just make a reference to that. Just make yourself familiar with it. All right, so I think in that sense, this problem is very simple because that is only to find the BC as a vector, divided that by the length of BC to give you the unit vector. That unit vector multiplied by 600, that give you force as an ijk. And then that reduces to something like fxi plus fj, fyj plus fzk. And with r, I'm taking OC. So OC is what? That is 2i plus 0j plus 0k, right? And then if I put that inside the determinant, the moment becomes ijk. And the first row is the position, that is 200, and then fx, fy, fz, and then you find. Either you find it by that, or you just use that formula we introduced yesterday. Do you want to see that formula? You want to see that formula? Let me show you the formula. So that was in yesterday lecture. So when it comes to the three-dimensional calculation of the vector, you either find this from the determinant, that is the determinant, right? But if you want to do it by the formula, yeah, that's a formula. That is the same. This is the extended version of the determinant, 3 by 3 determinant. If you extend it, you get that formula. But with this, you don't have to worry about the positive, negative. Positive, negative, when you extend the determinant, the chances are you make a mistake. It's a minus 1 plus I plus j, minus 1 to the power of I plus j. You can make a mistake with the sign. But that formula is simple to use if you have it. If you want to memorize it, that's difficult. You don't have to memorize because you bring your formula sheet with you to the exam. Questions? No questions. Let's move on. The answer, yeah. I didn't give you the answer. I simply went through the steps. Yep. Solve it? Okay, I solved it. No worries. So the only thing which I skipped was to find UBC. So let's start BC as a vector. BC as a vector. That is, you want to go from B to C. So if I'm doing that, I first go in that direction and then go along the X, and finally I go along J. So BC would be along the X, that is negative movement, that's minus to I. Along the J, that's a negative movement, that is negative to I, to J. And along the Z, that is again negative, that's minus K. Does that make sense? Yes? All right. And then what is the unit vector? First, I need to find the magnitude of BC. Magnitude of BC is 4 plus 4 plus 1, which is 3, right? So then my unit vector becomes unit vector of BC, that is minus 2 over third I, minus 2 over 3J, minus 1 over 3K, right? And then my force becomes 600 multiplied by that. And 600, that is minus 40I, minus 40, sorry?
400.
Is it 400? Yeah, 400, yeah, thank you. J minus 200, 200K. Is that right?
So
Okay.
when the I vector supposed to be equal to minus 2I is going to the from the unit vector.
Yes, unit vector. What about it?
I think 2 is equal to
2/3, 2/3, 1/3.
from the first step,
I.
from B to C.
Okay, yeah, let me see. You're saying that the I is positive, is it? Yes, you are right. That is positive. Thank you for that. Correct? Now your calculation would be like that. MO is equal to IJK 200 and 400 minus 400 minus 200. Can you do the calculation yourself? Okay. Calculation, solving this one. All right. So because I'm lazy, I do this by the formula, not expanding the determinant. So I'm bringing this formula here. So this is just plugging the numbers. That is MO is equal to RY. What is RY? That is 0. Multiply by FZ. FZ is minus 200 minus RZFY. RZ is 0 times whatever I, and the J component has a negative in front of it, minus the parenthesis Rx. Rx is 2. FZ. FZ is minus 200. And then minus RZ, that is minus 0. J. And finally, the third one is Rx plus Rx is 2. Fy is minus 400. And the remaining Ry is 0. K. So that is MO is equal to 0I minus 400 minus plus 400J. And this is minus 800K. So we have time for one more practice. 117. Okay, 117, let's try this one. Resultant moment for this system of forces. Okay, so what we can do is we can calculate the moment as a vector in different ways. So one way of that is, first I find the resultant of the FCFB, and then the position vector for that I can take R to be OA. And then the total rotation would be R multiplied by resultant. That's one way of doing it. The second approach is my moment with respect to the O, it has two components. The first component is R OA multiplied by FC plus R OA cross multiplied by FB. Is that clear?
Why R is open?
Because the position vector for FC, how many options we have for FC? FC, the position vector could be OA, could be OC, right? These are the points we have, which we have coordinate. Any other point could have been. And for the FB, the options are either OA or OB. So OA is shared between both of them. So that's why we use OA. Okay, which one you want? You want to do them separately or just, well, either way, we are going to have two unit vectors, the unit vector of AC, and we have to have unit vector of AB. So how do I find the unit vector of AC? I have to find AC and divide that by the magnitude of AC. Going from A to C, I go vertical direction of 6 meter negative, and then negative 3 meters and positive 2 meters. So that is 2I minus 3J minus 6K. And the magnitude is 4 plus 9 plus 36, which is 2 over 7I minus 3 over 7J minus 6 over 7K. Yes? And we do the same for AB. So AB, I choose a plan to travel from A to B. From A to B, let's pick a different color. So again, same Z component, 2.5 in the positive direction, and that's it. So that is 0I plus 2.5 j minus 6k, and that is root 2.5 squared plus 36, right? So this doesn't seem to give a perfect number. Let's do it again, 2.5. Yeah, that's 6.5. 6.5. So that is 2.5 times 6.5 j minus 6 divided by 6.5 k. Now we have the unit vectors. All you have to do is to find out the forces. The magnitude of the first one is 420, and the magnitude of the second one is 780. And these should be multiplied by their unit vectors. All right, now you have both forces, and then what you need is to find the position vector of OA. OA is simple. OA is 6k. OA is 6k, or in another term, this is 0i plus 0j plus 6k. So if I have to put them in determinant, to put that in determinant, that is ijk 006. For the first one, I put this, the product of that, 60 times 2 to 120, 210, 420, negative, negative, plus the second one is ijk 006, and the numbers are 0, 2.5 divided by 6.5. 0.38. Yeah, so this is Fy, Fz. I'm just late for attendance, sorry. So you just add them together. All right. The next thing is, let me finish the attendance, and then any question you have. By the way, my consultation is between now and 12:30. I'll be in a student hub. Any question you have, just come over there. I'm happy to help you with this. Yeah. You want to see the screen? Okay, okay, okay. Yeah, yeah, make it smaller. Thanks. All right. Natasha is here. Nguyen is here. Chaisal here. Daniel. Abdullah Enja here. Jonathan Away. Ahmad here. Nigel here. Barnaby here. Flynn here. Shah away. Darcy here. Horty here. Just let me repeat, guys, if you are coming to classes, I make sure you will have the best chance of passing these subjects, all right? Don't worry about things being complex. Just come to the classes. Yeah, that's my promise to you. If you don't come to class, I mean, Sehrish missed the class. What can I do for her? I can help her during the consult. The chances she get some part of the hint. The other part, if you miss the class, the chances are you miss the after hour works. But if you take this one, even if you miss the after hour work, you'll be okay.